All right, so today is our intro to Unit 7 discrete functions. We did a little activity to start out this lesson, so if you're watching the video, which I think a lot of you will be, you are going to pause the video and you're going to see if you can come up with as many things about this list as you possibly can. And then I want you to head over to YouTube and search up the TED Talk on the Fibonacci sequence. That's how we started out our lesson today. And that will tell you actually a little bit about this list. So see what you can come up with, pause the video, and then we'll head over to start the lesson. So we're working with what we call discrete functions. It would be helpful if we're going to do a unit called discrete functions if we know what a discrete function is. So we're going to start there. So discrete functions, we call these functions that depend on n, which brings us to our next question, what is n? But before we get there, discrete functions are typically discontinuous functions, meaning they're more like a set of points that is disconnected. So we actually don't connect all the points like we're used to when we graph a function. So we would call it discontinuous. Like a discontinuous set of points. And essentially, this happens by considering our x to be the term number, and then we graph this as an ordered pair with term number and term value. So for instance, this is term 1, term 2, term 3, term 4, term 5, and so on. And these terms have, oh sorry, I went too far back there. These terms have values, right? The value of term 1 is 1, the value of term 2 is 2, term 3 is 2, term 4 is 3, term 5 is 5, term 6 is 8, and so on. So we'd graph the term number as the x and the term value as the y. Okay, and then the follow-up question from earlier is that functions depend on n. So a discrete function is a function that depends on n. So what is n? That's the next question. N is essentially just a variable within our equation that we're going to be working with that is from the set of what we call natural numbers. So they're positive integer values, which means when I say the word integer, I mean like whole values. So they're essentially, what they end up being are the counting numbers, things that we've basically learned from our infancy, the regular counting numbers. So 1, 2, 3, 4, 5, and so on. So positive whole numbers. The set of natural numbers can be used with the notation, kind of like the set of real numbers has those like 2 bars on the R. The set of natural numbers has like 2 bars on the N. Okay, this n value that we're talking about is basically just kind of referring to the fact that we're going to have term values that might be decimals, but our term number, I can't have a term 1.5. I can have a term 1, 2, 3, 4, 5, 6, 7 in a list, but I can't really have a half term in between those. So for instance here, like if I had a list of numbers, some of them could have decimals, but I still have term 1, term 2, term 3, term 4, term 5, term 6. I can't have a term 5.5, right? There's no term in between that. So that's why it's dependent on those whole number values. Okay, and then a few more things that we need to know. What is a sequence and what is a series? So a sequence is an ordered list of terms that, and I'm actually going to change the word increase here. I want to change it to that change by a fixed amount. No, I've got another box here that needs to be deleted. Fixed amount, or I would say pattern. Okay, so what we just saw in our previous slide, that is a sequence. It's called the Fibonacci sequence. This has a fixed pattern that all the numbers are generated by. Okay, we found that pattern to be the pattern where the next number in the list is generated by adding the two previous numbers. So 1 plus 1 was 2, 1 plus 2 was 3, and so on. So that's a consistent pattern that develops our sequence. Okay, and then we're not going to touch on series today, but just so that you have kind of the setup information here. A series is the ordered list of terms from a sequence, but added together. So we call this the sum of a sequence. So far, so good? Okay, so today we're going to focus in on sequences. We're going to see a few ways that we can represent sequences with equations. If I wanted to find something like maybe the 200th term in this sequence, ideally I don't want to write out a list of 200 numbers, right? So how could I easily find the 200th term by not writing out all of those numbers, right? Paige?
You could add the,
Right. So the only way, because these sequences are kind of generated from previous values sometimes, or because they're generated in a way where we would have to write them all out, formulas are going to help us with that, right? So that we don't have to write out 200 numbers, and I don't need to know the 198th and 199th to continue my sequence, right? So this doesn't quite fit into the types of sequences that we're going to learn about today, but we're going to touch on this later when we learn about a different type of function. So for our sequences today, I have a couple examples for you. I want you to take a second and just pause here and see if you can figure out the main pattern for how we generate future numbers in these sequences. Okay, so I heard a few of you guys say the pattern for the first one. So how do we generate future numbers in this sequence here?
Plus 4.
We add 4. Okay, so the next number here is 30, right? Because we add 4 to 26. What about the second list of numbers here?
minus 4.
Yeah, we're subtracting 4. Anyone figure out the third list? Yes, this one's a multiple. So to get future numbers in this sequence, we're actually multiplying by 3 each time. Okay, so we're going to unpack these a little bit on some of the next slides here. So I just want to introduce to you first these first two sequences. And the first two sequences are what we call arithmetic, spelled pretty much the same as arithmetic, but the pronunciation is a little bit different. So arithmetic sequence, the first two are arithmetic sequences because they are generated by either adding a value consistently or subtracting a value consistently. We call this the constant difference. And I shouldn't necessarily say increase. They could also decrease. Increase or decrease by a constant difference.
Could you say change?
Yeah, we could say change too. Okay, so we're going to learn how we can express both of these guys here as general equations so that I could maybe find the 100th term in the sequence or something like that without having to write out the whole sequence. So first, I'm going to introduce to you the formula for an arithmetic sequence, and I'll just kind of break down what each of these things represents. We're going to learn quite a few different formulas in this chapter. What's important for us to know is, like, if I'm trying to find the 10th term in a sequence, it could be pretty easy for me if I have the first 4 terms just to write out the rest of the terms. If I want to find the 70th term, it's probably not worth my time to write out 70 terms. So those would be the cases where instead of writing out the sequence, I would use the formula. So sometimes it's going to be better for you and more efficient for you to just continue the pattern and find the term. Sometimes it won't be, right? If I want to find the 50th term, I don't want to sit there writing out all the values. So the formula will help me with that. Okay, so n. N is going to be the term number. So you kind of saw me refer to this n value earlier. Essentially, if I'm looking at a list, maybe I'll just hop on to C2 pages here so we can talk as we write these. So if I'm looking at the term number here, and I look over at my sequence from number 1, this is term 1, term 2, term 3, term 4, and so on. So when I say the term number, I'm talking about that term in the list of numbers, the 10th term, the 11th term, whatever. Okay? So this is always going to be a positive whole number because I can't have a term 1.5. That doesn't make sense. Okay, it's going to be from the set of natural numbers, like we said earlier. Okay, Tn is the value of term n. So if I say T7, I'm looking for the value of the 7th term in the sequence. Claire, do you want to put that away?
Yeah.
Thank you. Okay, so if I say in this example right here, number 1, what is T4? This is T4. 26 is the value of term 4. Okay, and this is a subscript right here. So the subscript just indicates like, oh, it's term 4, it's term 5. It's not like a multiplication or anything like that. A is the value of the very first term of the sequence, or in other words, T1. Okay, so if I know what the first term is, then hopefully the rest of my pattern can kind of just like explain the constant difference that we're going by, like the +4 or the -4. If I don't know where I start, how do I know how to generate the rest of the list? That would be pretty hard, right? So I need to know the starting point. And then the D value is going to be the constant difference value. So that can be your addition or your subtraction. And it will just be expressed as positive if you're adding or as negative if you're subtracting.
What if you're multiplying?
That will come next. That doesn't fit into what we call an arithmetic sequence. So we'll talk about that one in a couple slides. Okay, so we're going to find an equation to represent the sequence. And then for the second part here, I want us to find the value of term, let's say, 50. We're going to find the value of term 50 after we find the general equation. So I am looking to fill in two things in this equation that I just broke down for you guys. We need to fill in A, and we need to fill in D. Tn and n are going to remain as variables because the term number and the term value are always changing depending on what I'm looking for. But A and D don't change in the sequence. The first term is always the first term, and the constant difference value should always be the same. So what is A in this scenario?
14.
Yes, the value of term number 1 is 14. And what about our D value?
4.
Yes, so we found that we were adding 4 to get future terms. So we will sub in D as 4. This right here, just as it is our general equation for the sequence. Okay, now for part B, I just kind of tacked this on. We're going to find T50. Again, I don't really want to write out 50 numbers here in order to find term 50. So this is our really quick way of finding the 50th term. We're just going to sub in. So notice how this n and this n are the same variable. If I sub in 50 for the first n, I'm going to sub in 50 for the second n. And that should allow me to actually calculate the value of the 50th term there. Okay, so whatever gets in here. Sorry, I put 40 there. I meant to put 4. Okay, and then we're just going to calculate. So term 50 is equal to 49 times 4 plus 14. So someone can calculate that quickly for us. Marissa, what'd you get?
Got 2,744.
Anyone else? Jolie, did you do it?
I'm doing it.
Okay.
I got 210.
Ooh, okay. So someone got 210, someone got 2744. Let's check that one more time.
I worked with that plus 9.
So 49 times 4 plus 14, 210. All right.
Yeah.
And that is the value. If I were to write out all 50 terms of this sequence, that would be the value of the 50th term. Much faster than writing out 50 terms, I think, right? Owen's like, I don't know, I could race you. Okay, good. All right, so this one we looked at earlier as well. We decided that we were subtracting 4 to get future terms. So I want you guys to see if you can come up with a general equation. That will be part A here. And then I want you to use your general equation to find term 100. Okay, so I'm going to pause for a second. If you're watching the video, pause and see what you can come up with. All right. Can somebody tell me what they found for the first part here? What's the general equation? Paige, go ahead.
Tn equals 7 plus n minus 1 times -4.
Lovely. There we go. Especially important that we write this -4 with brackets around it because we want it to be multiplied and not subtracted from the n minus 1. So make sure you have your brackets around there, especially for the negative part, right? Okay, T100, what did you guys do to get T100?
7 plus.
7 plus.
7 plus 100 minus 1
Yep,
times -4.
great. Like this?
Yeah.
Okay.
Is -389.
Awesome. Good? Okay, everybody got that? All right, perfect. So the third example, what do we do when we have a multiple? Well, firstly, I can't set this up in the same way where we have like additions happening here. I need a different formula because it's being multiplied. So I have to have a multiple happening here for this formula. So when we set up this formula, n, tn, and a are all going to be the same as they were before. So this is still going to be the term number. This will be the value of term n. This will be the value of the first term, for T1. And then we have R. So R should indicate to you that we are multiplying because R is going to be our constant multiple. And even if we have a division, so we can actually still use this for divisions, but we have to express our divisions as multiplications. So for example, if you see a sequence and if you have a constant division by 2, I have to express this as a multiple. So how would I express a division by 2 as a multiple instead? If I divide by 2, what am I doing to my number? We're halving it. So that's the multiple. I would be halving it. My R would be 1 over 2. If I were dividing by 3, my R would be 1/3. Yeah. I'm taking a third of it, right? Nice. Okay, so in our previous example, we figured out that this was being multiplied by 3. So we're going to create a general equation, and then, so that's going to be our first part. And then I want to use that general equation to find, let's say, term, I'm not going to go too high with this, let's say term 18. Could we write out the rest of the sequence and find term 18? Yeah, probably, but we'll use our formula just to kind of practice with it. So A, I want to plug in A and R in my formula Tn and n will always remain as variables. So what is my a in this formula? That is the first term, value of the first term. And what is our r? 3. That's the constant multiple. And then I'm just going to have n minus 1 up here. Okay? That's our general equation right there. And then again, if I want to find term 18, I'll plug in 18 for both of the n's. And I'm going to be very careful about how I do bedmass here. What do I want to make sure I do not do here? What would I say is the biggest math crime that you could do right now?
2 times 3.
Yes, do not do 2 times 3. Okay? We want to do exponents first. So you're going to do 3 to the exponent 17 to start, and then you can multiply it by 2. Okay? Follow proper bedmass. It's going to be a pretty big number because when we have multiples, we are increasing pretty quickly. I'm going to turn this off now. What'd you guys get? Who can say this nice large number for us?
258,280,326.
Great. 258,280,326. Thank you, Paige. I chose one today where we got into the billions, so that was fun. Okay, so when we're doing multiples, we can either, like if we're growing by a multiple, like if it's times 3, we can get really big really quickly. If I'm doing something like halving it, I can get really small really quickly because these are actually exponential. Right? You guys remember the graph of exponential goes like up really high really quick. That's why we get such a high number here. Good? Questions? Anything? Okay, so we just want to remember bedmass here. Can I flip? Okay, so you guys are going to see, we'll pause it again for a couple seconds. You guys are going to see if you can come up with the general equation. So that will be the first part. And then I want you to see if you can come up with, let's say, the 15th term, term 15, but I want you to leave it in exact values. So exact value of term 15, so no decimals. Okay, so we'll pause it here for a second. Okay, can somebody tell me their formula?
270 times 1/3 n minus 1.
Great. So this is what you should have got. So be mindful. We are dividing by 3 here, so our R value needs to be 1/3. Okay? If you write 3 there, you're essentially saying that the list is growing by a multiple of 3. We don't want to say that, right? So you need to be careful with that one. Okay? When I go to find term 15, I'm plugging in 15 for both of the n's here. So we're plugging it in here and also up here, because these are the same variable here, right? So I want to make sure that I plug in the same thing for both of those terms. And we are going to have the 15 minus 1. Oh, sorry. I'm so sorry. Why didn't you guys tell me that this wasn't up on the screen? We're going to have the 15 minus 1 simplify to 14. And I just want to show you guys, I know not everybody has a calculator that will simplify this for you, and you should know how to do this by hand anyways. So I'm just going to show you guys how we can simplify this without needing a calculator to do it for us. So when I have 14 to on a fraction, an exponent of 14 on a fraction, that 14 actually gets applied to the numerator as an exponent and also the denominator as an exponent, which brings us to, what's 1 to the exponent 14? 1, yep. And then if we do 3 to the exponent 14, I'm getting 4,782,969. And then our job would essentially just be to find the greatest thing that we can divide into both of these. So we could try 270, but if I try 270, I'm getting a decimal for this value down here, so I don't think 270 goes in. We could try 27 and just see if that works for us. So let me just tape it in here. 696 divided by 27. Oh, that's still giving me a decimal. What else could we try that could potentially go into both of these? I usually like to think about the value 27. What things go into 27? 9. So I could try 9 or even maybe 90 in both of those things. Because of the 0 here, sometimes we can get like the extra like tenth on there as well. So 90, if I try that here, I'm still getting a decimal. What if we try maybe 30? Okay, 30 seems like a pretty big number. So if I divide this by 30, I get 9 left here. And then if we divide the bottom by 30, we get a decimal. Let me try that one more time. I thought that that one worked. 6 divided by 30. No. So what's the biggest thing that we can get in here then?
It's, you wrote the last, it's 4,782,969.
Thank you. Okay, so does 30 go in here then? Because I felt like 30 should have worked.
No, it's still 0.3.
Okay. So we need to find something that goes into both. Did 27 go in? Oh, 27 did go in. Okay, so yeah, 27 went in. I just had the wrong last two values there. 33? Does 33 go into 270 though?
No.
Okay. I think this is probably, I mean, you can always reduce it a couple times if you don't happen to find the biggest one. Like let's say you start with 3 and then maybe you notice, okay, I can do more than that. I can do a 9 as well, something like that. But I think this is probably about as low as we can go because 5 doesn't go in here and 2 doesn't go into here and 10 doesn't go in here as well. So I think that's our final value there. Okay. You didn't get that? What did you get?
1,260. Just that.
Did you do the opposite maybe? Did you accidentally do these reversed?
I just put it in my calculator, 1/3 to the power of 14.
Okay, so we're keeping exact values though. I think your calculator's giving you a decimal value, right?
Yes.
Yeah. Or does your calculator leave in exact values?
It's giving me 4.666667. Like 8 sixes.
But it's probably scientific notation as well, right? Does it say like times 10 to the something at the end?
No.
Okay, I'll have to look at your thing. Anyways, that's the end.